In the name of God, my name is Nasim Naseri. In this presentation, we will talk about protein-ligand molecular docking, especially about corticosteroids. Molecular docking is a way to predict the activity and affinity of ligand to its receptor. Molecular docking studies are used to determine the interaction between two molecules to find the best ligand orientation in the complex with minimal energy. The docking of protein ligand is a process with four general steps. First, preparing the ligand. Second, preparing the receptor. Third, doing molecular docking. And fourth, analysis. Following, we will see this process about cortisol and glucocorticoid receptor. At first, for preparing the ligand, we can use PubChem database. In this box that you can see, we type the name of our ligand, mean cortisol, and then you can get a lot of useful information about your ligand. And then we should save the 3D structure or 3D conformer in SDF format in this database. The second step is preparing the receptor that we can use two databases for this purpose, UniProt and PDB. In UniProt database, type the receptor name, that here our receptor name is cortisol receptor, and then you will get a list of proteins, and you should choose one of them, the most appropriate them according to your desired species. Here we chose the glucocorticoid receptor for a human, actually a Homo sapiens species. Then the UniProt will give you a lot of useful information about your protein, such as sequences. If you click on FASTA or FASTA, you can get the sequence that you can copy it. So copy the sequence and go to PDB database and click on search in the toolbar. And then click on sequence search and then paste the sequence that you copied in this box. After this, PDB will give you a list of proteins that you have to choose one of them. Please choose the item that the X-ray diffraction is less. Here we chose for UDD receptor. Then for doing some changes on receptor and also doing molecular docking, we use UCSF Chimera software. In this software, at first we should do some changes on our receptor. Then for calling the receptor, click on File here. Click on File here, and then you will have this box. Click on PDB and type the PDB ID of your protein that you choose in PDB. Here we've typed for UDD. Okay. Now we have to remove the excess molecules that are co-crystallized with main protein, that we don't need them. So for this purpose, click on select and then click on residue and then all non-standard. Then you will see that the excess molecules are highlighted. Then for deleting them, click on action, atom and bonds, and then click on delete for removing them. But some other changes must perform on receptor. For example, deleting the water molecules, adding net charges to amino acids, complete the incomplete protein chains, and finally adding the hydrogen atoms. For this purpose, we do dock prep. So click on Tools and then click on Structure Editing, click on Dock Prep, and in this box click on in this box click on OK and wait till the dock prep to finish. After finish that, save your new file with edit extension. Here we saved our file to name foruddd.edit. Okay. The last step of preparing receptor is minimization. Actually, we should reduce the energy level of our receptor. For this purpose, click on Tools and click on Structure Editing and click on Minimize Structure. For getting the best minimization, set the first box to 1000 here and set the last box to 100. So the first box to 1000 and the last box to 100. Then click on Minimize and wait till the minimization to finish. But then after finishing the minimization, you can click on File and then save this file in min extension to PDB format. Then open the prepared receptor and our ligand in Chimera. So you can click on File, click on File, and then click on Open and choose your receptor and ligand from your computer. For getting the best docking, please highlight the amino acids of active site. So you should find the amino acids of active site from PDB or articles and then click on Favorites, Sequences, and in this box you should highlight and select that amino acids of active site, and then if you click on Actions and then click on Show, you can get the amino acids of active sites in highlight format. For change the colors of our complex, click on Presets and then click on Interactive 1. Then you can find the amino acids of active site more better. Okay, it's now time to doing Autodock Vina. For this purpose, click on Tools and then Surface Binding Analysis and then click on Autodock Vina. You will have this box. That's so important box, and we should do some changes on this box. At first, give a new name and determine the address of output file. Then choose the receptor and ligand from here, and then click on Resize Search Volumes Using. So click on Resize Search Volume Using. Then you can select one way to moving this green box. Here we choose Control and button to our mouse. Then if you click on this empty space, black empty space, you can find this green box. So Here, if we press the control and button 2 at the same time, we can move this box and fit it around the amino acids of active site, like this. Okay. Then the other chains are receptor options, ligand options, that all of them must be on true. In advanced options, all of these numbers must be in maximum level, and in the executable location, if you have downloaded the Autodock Vina software before, click on local and then give the address of this software from browse. But if you don't have this software on your computer, click on Opal Web Service. Then the camera will call this software Autodock Vina from internet. Then click on OK. And wait till the Autodock Vina finished. After this, you can get the results of docking in this box, and camera will give you some poses of ligand. But for selecting the the best matched of pose, you can click on H bonds here, and please select the pose that has the highest number of hydrogen bonds. Then it's now time to save the new complex. Click on favorites, model panel, and click on copy combine. Then select the ligand file, receptor file, and the best pose that you've chosen. And then give a new name, and then click on OK, and then click on file here. Click on file and save it in PDB format. Okay, the results of our docking is ready now. It's time to analysis. For analysis, we can use two sites: protein ligand interaction profiler and PDB-Sum. Here we use the protein ligand interaction profiler. You should upload your final file of docking in this box, and then click on analysis. So here we can get a lot of information about your docking, actually the results of analysis, that are some charts and some photos. The two most important charts that you can find are hydrophobic interactions and hydrogen bonds and their features. For example, about hydrogen bonds, you can find the distance of donor acceptor and the amino acids of them and the number of amino acids. And here we can find the 3D structure of our final complex, and here we see that this complex has 3 hydrogen bonds, and we can find these bonds, 3 bonds in this 3D structure. To better know the use of docking, we here compare the docking of cortisol with other glucocorticoid betamethasone. So we should do all the steps above. At first, get the betamethasone ligand from PubChem and save it in SDF format. Then do molecular docking with the UCSF camera. Notice that here our receptors are the same, and for both ligands are 4UDD. So here our ligand is betamethasone and our receptor is 4UDD. And here we get the best pose of docking and save it, and then use PLIP or protein ligand interaction profiler for analysis. Okay, here we get the results of analysis. You can see that the docking of betamethasone in 4UDD receptor has 8 hydrophobic interactions and has 5 hydrogen bonds. And this is the 3D structure of complex with 5 hydrogen bonds. With comparing the results of betamethasone and cortisol analysis, we can find that the number of hydrogen bonds and hydrophobic bonds in betamethasone are more than cortisol in both of them. In the cortisol, hydrogen bonds that are more important are 3 bonds in cortisol, and in betamethasone they are 5 bonds. And in about hydrophobic interactions, in cortisol we have 6 hydrophobic interactions, and in betamethasone we have 8 hydrophobic interactions. So we can conclude that the potency and affinity of betamethasone both are probably more than cortisol, and this conclusion is consistent with the content of this table, which shows comparative oral corticosteroid potencies. Thank you very much.